Okay, guys, let's talk about how these pieces of secondary structure form larger three-dimensional structures that we're going to think of as actual functional proteins. Now, there are two in general, there are actually now three, really, when you think about it, general large classes of proteins. The first, so-called fibrous proteins. That's what we're going to talk about next. Second is the so-called globular proteins. We're going to spend most of our time. And over the last 15 years or so, a new class of proteins has been recognized, the so-called intrinsically disordered proteins. Or IDPs. And we're not going to have time to talk about those guys at all. They wouldn't quite fit in our discussion about order and so protein structure because they don't have any. And that lack of structure is actually really critical to their function. It's a fascinating topic, but for another time. Okay, so we're now going to talk about how these elements of secondary structure lead to the formation of a particular class of protein that are highly extended, and they're generally built this way because of a need for particular mechanical or physical properties. These proteins are often structural or play particular structural roles in various ways in organisms, right? And the reason we're going to talk about them is because of some of the ways in which they illustrate some interesting aspects of how secondary structure leads to certain three-dimensional structural properties, right? So fibrous proteins, as I said, are generally elongated. They mostly play these structural roles. And the interesting thing about them is they introduce you to this idea of the mapping between primary sequence and larger three-dimensional structure. And in the case of fibrous proteins, this mapping is relatively simple. In general, fibrous proteins can be built out of very simple repeating patterns of particular amino acids that get repeated over and over again, right? Globular proteins, by contrast, are a much larger class of proteins. They're compact structures. There's no real systematic pattern of repeating amino acids in most cases, though people have figured out how to build globular proteins with certain types of patterns. In nature, they don't seem to occur that way. And they generally have a well-defined inside and outside. That's a bit less clear for the fibrous proteins. So let's take a look at a few examples of some fibrous proteins. The first one we want to talk about are the so-called keratins, or the alpha keratins. This is a super important protein in hair, right? Your hair and your fingernails and in your skin. They tend to be very long. The fundamental alpha keratin is about 300 amino acids, and it's mostly all alpha helical. It's got some globular bits on the ends, but it's mostly a giant protein alpha helix like we just talked about. The fascinating thing about the alpha keratins is they're built from a really simple repeat pattern, and this is more or less what it looks like. Hydrophobic, and specifically a small hydrophobic, small aliphatic, like isoleucine. All right. I should say leucine or alanine, for example, but not glycine, right? So a small aliphatic, like these guys. Many other types of amino acids, but not proline and not glycine. Another one of these small aliphatics, and then three other can be variable types of proteins, right? And it's that pattern that generates what we think of as the protein fiber that makes hair, alpha keratin. So the question then becomes why, right? And the reason, if you think back to that structure, the alpha helix, is explained in how this repeat, so-called heptad repeat, right? So it's 7 amino acids in repeat, right? So there's this hydrophobic, 2 amino acids, another hydrophobic, and 3 more amino acids, and the pattern repeats again. All right. If you think about how those amino acids are going to propagate around the alpha helix, something very interesting jumps out at you, right? So here, let's say this A amino acid, right? We're going to show that right here, right? And we think about going down an alpha helix. Remember, how many amino acids does it take to come kind of most of the way back around? A little less than 4, 3.6, right? So here's A, here's B, C, there's D, that a next hydrophobic amino acid. And look, we're back over here in about the same spot, not quite, a little less, right? But over here on a sort of about the same face of the alpha helix. And then we could go down again. The next hydrophobic amino acid would then show up, right? And what this pattern, this heptide repeat pattern, because of the alpha helical repeat, is going to do is bring the hydrophobic amino acids around to about the same face of the helix. But because the helical repeat isn't perfect, they're slightly offset. You end up with a stripe of hydrophobic amino acids shown here in red that coils around that alpha helix, right? So remember, the alpha helix is a right-handed helical pattern. So you have this right-handed hydrophobic stripe that propagates up along the alpha helix. Okay, now that's on the surface. Remember, the amino acids are exposed. So all of these hydrophobic small aliphatics are sticking out. That's not generally where they want to be, because we just learned, thinking about the hydrophobic effect, that there's a driving force to make that stuff kind of clump up, right? To cluster up. So if you get two of these guys together, those hydrophobic stripes are going to want to interact with each other, because that's much more energetically favorable. And when they do, those two right-handed helices then make a left-handed superhelix. As these two alpha helices wrap around each other following that hydrophobic stripe. This is, of course, known as the famous coiled coil, even before then known as a leucine zipper, where it was first identified. And that coiled coil is a super important element in putting bits of secondary structure together, specifically getting pieces of alpha helix to interact. And you don't have to just stop with 2 alpha helices. In other types of secondary structure, you can put 3, 4 alpha helices together into these coiled coil bundles. All right, so keratins illustrate this idea with just a pair of helices, a simple 2 helical coiled coil. All right, and then, of course, when you start putting these guys together, there's that keratin dimer, that coiled coil, and there's those little bits on the end. Look how long this thing is, right? It's 450 angstroms, and it's extended dimer. You then stick these guys together. The helical domains at the ends kind of interact with each other. They also begin to interact laterally to form a protofilament. You start putting protofilaments together. You make microfilaments, then stack together, and you build these guys up. And next thing you know, you've got a piece of hair, right? Now, it's interesting. You think about it, what I just said. The formation of this structure with that alpha helical structure, the way I described it, builds a really pretty flexible, right? Nice extended fiber that is incredibly useful for making hair, right? Elements of skin and stuff. But I also said keratin is the principal component of nail, your fingernails, your toenails. It's also the main thing that composes a rhinoceros horn. And a rhinoceros horn is strong enough behind, however many 2 tons of rhinoceros to punch a hole through the side of a Jeep. So how could something that, is basically the same thing as the hair on my head be turned into something that strong, that hard? Well, the hint is that keratins contain a particular type of additional modification, right? Falls into that class of primary sequence, right? But in this case, it's putting bits of these guys together. It's a particular type of additional covalent interaction. It occurs between the same type of 1 amino acid. I'll give you a hint, specifically between cysteine residues, right? And that particular interaction is, of course, a disulfide bond, right? So keratins are full of disulfide bonds. Okay. And as you increase the amount of disulfide cross-linking, you can dramatically increase how rigid these larger structural fibers happen to be. Okay. So let's think about another example of a fibrous. This is not the only way to put a fibrous protein together. There are other ways to put them together. Um, so another example of a fibrous protein is silk fibroin, right? This is the fibrous protein that's produced by silkworms and by spiders, right? Super important fiber, and it's one of those fibers, if you remember, has phenomenal tensile strength per gram of mass or per unit of mass. It has a higher tensile strength, I believe, still than any um, fiber human beings have ever been able to create out of carbon or out of anything else. Silk fibroin still, I think, has the record per unit of mass in terms of tensile strength. So it basically is phenomenally strong. This protein is also put together by a relatively simple repeat pattern. In this case, instead of that heptad repeat, silk fibroin is built by a simple alternating repeat of serines, glycine, alanine, gly, ala, right? Where there'll be a serine in some positions, and then a lot of ala, gly. This every other amino acid is a glycine residue. Now, that peptide sequence is not going to make an alpha helix, but what it's going to be very good at making is a beta sheet. So if you take that polypeptide that's made of that simple pattern, you stretch it out, you get a couple of the guys and bring them together, you'll make a nice beta sheet. And silk fibroin is made by anti-parallel beta sheets, right? These guys then, as you stack these together, where are the amino acids going to go? Those glys and serines. They're going to go up and down, right? So if you now imagine taking a whole series of those beta sheets, right, stacked laterally to each other, and now you start stacking them on top of each other, what's going to happen is those side chains can interdigitate, and because of that repeating pattern, what's going to happen is they're going to stack in a particular way. If you take sheets that have the glycines, and you put those guys together, the glycines will snuggle down. Those polypeptides are going to get nice and close to each other. On their opposite sides, they're either serines or alanines, right? And ones that have alanines, you stick those guys next to them. The alanines are going to make, oh, nice van der Waals contacts with each other, right? Those nice London dispersion forces, they're just going to snuggle down there right together, right? And you keep stacking those things up with the beta sheets running in the propagation direction of the fiber. What you end up generating is a fiber, as you stack more of these guys up, that will not slide. The sheets won't slide relative to each other, right? It's sort of like if you imagine taking two pieces of Velcro, right? And you stick them together, and now you put, sort of a handle on there, and you try and pull them away from each other, not off each other, but laterally away from each other. It's fantastically hard to do. It's why Velcro is so incredibly useful. And that's held together by thousands, millions of tiny little hook and loop things that individually are so ridiculously weak. But you put them together and you orient them that way, it's almost impossible to slide them against each other, right? Silk fibroin is the same way. It's the reason that lateral in the fiber propagation direction has such phenomenal tensile strength, because there is so much stabilizing energy between these sheets stacked up this way that the only way to break a silk fibroin fiber in the fiber propagation direction, the long dimension, is to break in a covalent bond. So they're fantastically strong. But because those interactions aren't covalent and they're not really ordered, they're squishy, the sheets can slide laterally relative to each other, which makes them incredibly flexible in sort of torsional or bending directions, orthogonal to the direction of stretch of the fiber, right? Which makes this incredibly flexible, but incredibly strong fiber. Okay, one more fibrous protein example. This is a super important protein that has different mechanical properties, either from keratin or from silk fibroin. And it's super important for your skin, even more so than keratin for using, well, or at least as important. There's even more of it. It's super important for your bone matrix. And it's super important for tendons, connective tissue, all kinds of other things, right? In fact, it's the most abundant protein in vertebrates. And this is, of course, collagen, right? So collagen is put together in a particular way that is distinct from how either of silk fibroin or alpha keratin. But again, it's a simple repeating pattern. So in this case, the simple repeat pattern is a gly. and then 2 additional amino acids, and then you'll have a gly and then 2, right? And the repeat pattern is this. The glycine in this 3 helical repeat is invariant. The glycine's almost always there, I think. It repeats exclusively. X is frequently, not always, but very frequently proline. And Y is also frequently proline or very often hydroxyproline. So what you end up with is something that's very similar to glypro-pro, right? As for a long part of this helix. Now that's not going to make an alpha helix. All that proline, that's not going to be able to make a beta sheet either. What this simple repeating pattern does, though, is it forms a helix, but it forms a helix that's very similar to a polyproline helix. In fact, it forms a left-handed helix with a helical repeat of about 3.3 residues per turn, so slightly more than that repeat per turn. But instead of being right-handed propagation, it's a left-handed propagation, right? And these helices, 3 of these helices, or that single amino acid, that one single amino acid, that single chain is sometimes known or is referred to as tropocollagen, right? You put 3 of those guys together and they wrap around each other to form a right-handed helical coil with 3 tropocollagens wrapped around each other. Now, unlike with the keratins, where that coiled coil was held together by that hydrophobic stripe as those helices wrapped around each other, in collagen, tropocollagen, what's holding this helical unit together is a set of hydrogen bonds right down here in between the glycine residues, right, the backbone of the glycine residues, down in the core of the protein, right? And the reason that glycine is so critical, right, it's basically just supplying an amide and some carbonyls, right, along with the sort of the carbonyl of the proline in some cases, right? Well, the reason the glycine is invariant is because you couldn't get these helices that close to each other to form those hydrogen bonds in the core if there was a side chain there. So the reason the glycine is invariant is it's essential to form that hydrogen bonding network down through the core of this tropocollagen triple helix. Okay, so similar theme though, once you've got the tropocollagen formed to form the larger polymer we think of as collagen, you take that tropocollagen triple helix, you start stacking these guys up laterally to each other to form microfilaments, and then those stack together and you form these large, very elastic, strong and really elastic fibers that are so important for skin and for bone matrix and for connective tissue, other connective tissue like tendons, right? Okay, so with that, we're now going to turn our attention to globular proteins.